Hello, everybody. Welcome back to our class for geometry. And today we will be talking about section 2.5, which is on the infinite rulers. Originally, I want to put in 2.5 and 2.6, but I'm going to go ahead and split that into two videos because it might be a little too lengthy if I actually just put it all into one. So just make it so that it's not so overwhelming, right? So here it is. These are the three things that we're going to be focusing on for today in section 2.5, which will be postulate 2, the ruler postulate, postulate 3, which is the ruler placement postulate, and finally, defining what is the word between mean when it comes to points and in geometry. So all the stuff underneath for section 2.6, we'll go ahead and save for next time then. Okay, so let's go ahead and scroll down to the section 2.5 stuff that we're going to be talking about, okay? So here is postulate number 2, which is another name for the ruler postulate. Now, for this postulate, it says three things, and basically means that you can use any of those three. So the first one says that to every point on the number line, that there corresponds exactly one real number. So here underneath it, you can see that I have drawn a line, which is going to represent my number line in this case. So let's say that, for example, here for the number line, I'm going to go ahead and say the middle is going to be 0. Now, to any point that I find on the number line, there should be a number that goes with it. So for example, somewhere over here, maybe we'll go ahead and call it point A. If I look on maybe like say the ruler or the number line, that could be like say 3 units away. Or over here on the left-hand side, maybe I can say that this is going to be point B and it's going to be assigned the number that is -1. So any point that you pick on the number line, there should be a number that goes with it. Now, does it have to be a whole number? The answer is no, because I could pick a point that is closer by or a little bit further away, and it could be like, say, 3.2 or whatever. But nonetheless, you should always be able to assign a numerical value to any point on the number line. So second part of this postulate number 2 says that to any real number, actually, that should say, there corresponds exactly 1 point on the number line. So this right here, number 2 of this postulate number 2 is that it's the converse of what I just said, meaning it's the reverse of what I just said in part A. So if you remember back in the logic section, if I have A implies B, then right here, this right here is going to say B implies A. So that's the converse of it. And in this case, the converse is actually true because if I take any number, right, on the number line, I should be able to call it one single point then, okay? So if I have, like, say, the number 5.2, there should be only 1 point on the number line that is assigned to that number 5.2. Or if I say the number 0, there should be only 1 point on the number line that should be assigned to that number 0 then. Okay, so those are converses of each other. Now, the last one says that the distance between one point to the other on the number line is the absolute value of the difference between the corresponding numbers. So this is going to be referring to back to last time when we were talking about how to find the distance between two numbers using absolute value. And here it's telling us what the formula is. So here you can see I drew the number line once again, and I'm going to go ahead and assign some numerical value to some points then. So underneath it, I want to find what is the length of, let's say, CB over here. And keep in mind that when I say CB, I don't mean C times B, like say two variables multiply by each other, but rather the length of that segment CB that is shown right here on the number line. So according to this postulate, then what we're going to do is take the difference of the number, so which is going to be 3 minus 1 because those are the numbers assigned to it. And I'm going to go ahead and take the absolute value of it. So the answer is going to be equal to 2. Now remember, distance is always positive, so that's why we take the absolute value of it. And then that's where it's supposedly all come from then. So let's say this time I want to find what is the length of B to A. So what we can do is we can take 3 minus negative 3.1 and then absolute value of that. So that would give us, let's see, absolute value of 6.2. So that's equal to 6.2. Can you go the other way around? Sure, definitely. You can go ahead and say negative 3.1 minus 3 absolute value, and then that will give us negative 6.2 absolute value, which will give us exactly the same thing. So BA and AB, they're interchangeable in terms of like which one you want to subtract first from the other one, because all you're doing is taking the absolute value afterwards. Now, postulate number 3. Now, postulate number 3 is going to be built off of postulate number 2. This one is called the ruler placement postulate, okay? And now keep in mind that these two are actually related to each other, and here's how we work it. This one says, given that you have 2 points P and Q, the coordinates can be chosen such that P is 0 and Q is positive. Seems very trivial for the most part, but here's what it says. Okay, here's the number line once again. We have point P, which is going to be assigned with -7 on the number line. Let's say we have Q, which is going to be on the number line, which is assigned to number 3. Now, according to what we just said about postulate 2, we can find the length of PQ, which you can probably see is going to be -7 minus 3 absolute value, which is equal to 10. Now, this postulate basically says, hey, you know what? I don't want to work that hard. Instead, what I'm going to do is I'm going to reposition P and move it to the right of the ruler so that it's located at 0 instead. Okay, I'm going to reposition P so that it's going to be located at 0 instead of -7. And then that means that Q is going to be pushed forward to a positive number, and that positive number is most likely going to be 10. So in short, well, why is it that we have this thing? Because, you know, this is like very trivial for the most part. Well, if you consider the name of this postulate, the ruler postulate, it just basically means this is how you use a ruler, right? If you're trying to measure the length between one point to another with a ruler, you're probably going to assign one point equal to 0, and whatever the other point is, that's going to be the length. So that's all it is. All right, so those are my two postulates for section 2.5. And now I have a few questions, and that'll pretty much be it. So the very first question is this. If you have two segments, we'll call one AB, the other one is going to be BC, is the result such as the following? Is AB the segment plus BC the segment equal to BC the segment? So it's kind of like, I guess almost like a transitive property in a way, okay? Is that always going to be true? Well, one might think, okay, well, if A is located over here and B is located over here and C is located over here, yeah, that definitely looks like it's true because this piece over here plus this piece over here is going to be equal to the big piece over here. Well, that's only if they're on a straight line. So then that could be problematic then. Well, if they're not on a straight line, then that definitely cannot be true then. So maybe I have something like the following then. Let's say A is located here, B is located here, and C is located over here. You'll notice that AB is located over here, BC is located over here, but AC is actually the other side of the triangle, which is not going to be equal to each other. So the conclusion is only if A, B, and C are collinear, okay, meaning that they all have to exist on the same line. That's the only way for this equation to be true then. Well, let's go ahead and define some of this stuff right here then. So here is the definition for the word between that we're going to be looking at. Here we have point B is considered between point A and point C, and we denote it by this little notation over here. So it's kind of like A minus B minus C. So that is another way of saying point B is between A and C. If and only if what two conditions are true? Well, according to what we just said over here, then that means that A, B, C are collinear, just like we said in the picture over there. And if you notice our equation right there, well, that's the other part that's true, okay? AB plus BC is equal to BC, okay? So in this case, you can see how that actually works out because if I drew a picture of that, yeah, that definitely has to be true then, okay? So once again, A, B, and C are collinear to each other, meaning that there is exactly one line that contains them, and they have to be in the order so that I can take AB, the length of it, plus BC, the length of it, and that's going to be equal to AC, the length of it. Oh, let me make a mistake right here. That's going to be changed, so that's going to be AC over there, okay? So if I were to kind of change it around a little bit, let's say that I write it this time as like R dash T dash A right here. So if I say that this is true or if this is given, then what you can get out of it is that R, T, and A are collinear, and also that RT plus TA is equal to RA. Okay? All right, so that should do it for section 2.